All right, this is the second kind of problem that you commonly see with exponential growth and decay and differential equations. This is a radioactive decay problem. So you get something like this. The half-life of radium-226 is 1,590 years. Given a sample of radium-226 with mass 100 milligrams, first they're going to ask you to find the formula for the mass of the sample after t years, then find the mass of the sample after 1,000 years, and when will the mass be reduced to 30 milligrams. So let's go back a second. Half-life of the radium-226 is 1,590 years. So that means that m of at 1,000. If we have suppose we have a formula. We're going to look for a formula. It's like m of t, right? Tells us what the mass is at after some period of time. Well, we know that it's going to be after we know this at 1,590 years. It's going to be 1/2 of whatever it was when we started, m0. We know that it's proportional, and this is something we just have to know, that it's proportional, so that the change in mass over time is k, some constant k, times m, which means that m, and its k is going to be negative because it's decaying, so m is going to be m0 e to the kt. This is like the same, we're doing the same separation solution kind of thing. And to be fair, to be honest, in case you're probably starting to wonder this, other than this part right here, which we've already done once, and once we've done it once, we don't have to keep doing it, solving this problem, dm over dt equals km, turning that into an explicit problem of m equals m0 e to the kt. After that, there's no more calculus involved. And in fact, these are the same problems you probably did in Algebra 2, although the algebra might be a little bit more complicated. But it's nothing really different. Part A, right? Find the formula for the mass of the sample after t years. We're just looking for this general formula, mt, and we want to find m0 ekt, right? So we know m0. We know that it's 100 milligrams. M0 is 100. And what else do we know? Well, we know, like I said, we know that m of 1,590 equals 100 e to the k times 1,590, right? Just plugging that into the formula. And we also know that it's going to be 50, because that's what the half-life means. It means that the sample has decayed by half. So now where we started with 100, now we have 50. Okay, now we're going to solve this equation here. 100 e to the k times 1,590 equals 50. And we'll do it just like we did before. So e to the k times 1,590 equals 50 divided by 100, or 0.5. And keep going, right? We'll get k times 1,590 equals ln 0.5. And then, so k should be ln 0.5 over 1,590. Okay, what does that equal? All right, well, it's really, really small, and that's because it takes a really, really long time for radioactive material to decay. I get negative 4.36 times 10 to the negative 4. So, right, negative 0.000436. And that makes sense. It's very small, and it's negative. It better be negative. If it's not negative, we have a problem, right? Because it's decaying. It's not growing. Thank God. All right, so that's part A. I'm going to do part B over here. So B says, use that. So you're going to use that formula to find the mass of the sample after 1,000 years. So this is going to be just like the problem we did with exponential growth. We're going to do the same thing. So m equals 100, m0, times e to the negative 0.000436 t, where t is, what did they ask for? 1,000 years. Okay. And you'll just plug that into the calculator. It should turn out that it's more than 50, right? Because we know that it takes 1,590 years for it to get to 50. So after 1,000 years, it shouldn't be down to 50 yet. It shouldn't be down to half the original size. So you can do that in your calculator. I'm not going to worry about it right now. And when will the mass be reduced to 30 milligrams? Okay, so again, we're setting up the same problem. We want to know when the mass is 30, and we'll use this same model, negative 0.000436 t. And we'll solve for t. Oops. To cut to the chase a little bit, what are we going to get? We're going to t equals ln 30 over 100 over negative 0.000436, whatever that turns out to be. Okay, and it should be more than 1,590 though, right? So do a kind of plausibility check there. It should be more than that because it takes 1,590 years for it to reach 30, to reach 50. So it should take longer for it to reach 30. All right, so that's radioactive decay. You'll see that all the time. You can see once you've done, I mean, it's just like the problem we did with exponential growth, except that k is negative this time.